All right, so this is a very simple question, but not simple if you don't know. If you don't know the answer, of course, it's not simple. But I'm not sure that we really talked about this in great detail. So this was part of your review, so hopefully you took the time to kind of figure it out. But anyways, the one thing that's important to understand is that when you are dealing with a normal distribution, the probability of getting exactly any value is 0. So this has a probability of 0. But the probability of getting greater than or less than a value is never going to be 0. It's essentially 0 if you get far enough away. Like, what's the probability of getting a z-score of -50 or greater or less? You know, it's practically 0, but technically there's like 0.0 something, right? But the probability of getting exactly a value is, yeah, it is going to be 0. So that's just a simple conceptual thing. All right, here, I'm not going to go through all these answers, but essentially what's best approximated by a normal model, you just want to look for something that's going to have a unimodal. You already know what the normal model is, but you want it to be unimodal, symmetric. You want to have no outliers, no skew, so symmetric, like I said. And basically, which one of those will fit? And there you go. You can see some examples there. And you know, if we read through, you can find out the best one. If you want to know the specific answer, we can spend more time on that, but I'll let you guys get thinking about that. This is one that's worth spending a little bit more time about on. So we've got a normal distribution, and we want to figure out if there are 50 observations in this data set, how many would we expect, if they're normally distributed, how many would we expect to fall in the range A, B, C, and D? Now, what's not being shown here is that the sample mean's right in the middle. Of course, you already know that. And so this is going to represent, according to our empirical rule, that's 68%, and then 95%. And then beyond that, we would just expect whatever's left over, essentially. So this is only going to represent, 2.5% up on top and 2.5% on the bottom. All right. So here's the thing. If we know there's 50 values, then we should expect 68% of those 50 values. So 0.68 times 50 is 34. So we would expect 34 to be in this range C. And there it is. And honestly, that's probably all you have to do, because that's the only one that has that option. And then anything beyond that is going to be whatever. I can't think. But right here, if we go from 68% and we've got now 95%, we want to figure out how much is in this range for D. And that would be the same for B also. So if we've got 95% minus 68%, that's going to come down to, what is that, 27%. And then we want to divide that by 2 because it's split into 2 different regions, B and D. So that gives us 13.5%. So 13.5% of the data is going to fall in this range. 13.5% is going to fall in that range. And this is probably overkill, but now if we do 50 times 0.135, we're going to get close to 7. 6.75. So we expect about 7 values in those 2 ranges. So we're good to go. But it's just different ways of applying the empirical rule. Any questions so far? Oh, sorry. It says right here at the very top, there were 50 observations. Yeah. Okay. Is everyone having a blast? Is this the best way of starting off? Well, it's not your first day in class, but it feels like the first day. Let's see. This is one they just want us to plug in. This looks complicated. I mean, not really, but I mean, it looks complicated in the sense that there's a lot of different numbers to be plugged in. So essentially, they're asking us to fill in the z-score. So the z-score is, of course, your value minus the mean divided by the standard deviation. Now we're going to do some substitutions before we just jump right to the answer. So in this situation, we've got, according to government data, 22% of children in the United States under the age of 6 years live in households with incomes that are classified at a particular income level. A simple random sample of 300 children in the United States under the age of 6 years was selected for a study of learning in early childhood. I don't know if I read that right. In the government, or if the government data are correct, which of the following is best approximates the probability that at least 27% of the children in the sample live in households that are classified at a particular income level? Okay, so there's a few things that you can do right off the bat just to narrow down your answer choices. So we know that the government data represents the population proportion. So population proportion is going to be the 0.22. The sample, or sorry, the sample proportion, there we go, is 0.27. Because this is talking about 27% of the children in the sample. All right. Now the mean of a sampling distribution of sample proportions is the same as the population proportion. So this is going to be 0.22. So here's something I can plug in right away. The value of interest is 0.27, and the mean for this is going to be 0.22. So just with that alone, I can cross out 2 of my answer choices. So if I know nothing else, I can rule out two of these. Now, the standard deviation for a sampling distribution of sample proportions is P times 1 minus P all over sample size. And again, that's just one of those formulas that you have access to. You don't have to have it memorized. So my population proportion is 0.22. The 1 minus 0.22 is going to go right there. And the sample size is 300. Now, we can already kind of see what the answer is going to be based on this. We're not looking at 50-50, so that's out. It's not 0.27, so we've already got our answer, but you know, the 1 minus 0.22 is 0.78. So there we go. Now, it's just super, super important, and that's the main takeaway. And I know I've said this already, but it's been a while since I said it. We are moving forward, we're dealing with samples that have been taken from populations. And we're trying to figure out, is this sample result unusual, or is it something we'd expect? And the way we would say that, is it statistically significant, or is it not? And we're not looking at individuals saying this person is especially, is an outlier, but is this sample an outlier compared to what we'd expect? And so to that end, we need to recognize that we're always going to be working with sampling distributions moving forward. The other nice thing about sampling distributions is that they are, as long as they meet criteria, they are always approximately normal. Especially with means, as long as you have at least 30 in your sample size, they're always approximately normal. Population distributions frequently are not. Okay, let's see. I was going to skip this one. Let's see. I haven't looked at this in a while. So let's see what this one's all about. My son plays on this iPad and he gets it kind of nasty sometimes, so clean up his mess. There it is. Okay. In a recent Oh yeah, I'll tell that. I did not break my son's leg. Just this is being recorded, so.
Oh.
Okay, so back to some statistics. Let's see. I haven't even read this question to understand what's going on. We got a proportion of adults who indicated mystery as their favorite type of book. Now, this is one thing that's good to be aware of right from the beginning. Eventually, we're going to get to a point where we are doing some inference testing, and you're going to have to pick what's the proper test for me to do, and therefore, how should I set up my equations? And I'll give you guys a heads up right now. It's going to come down to using essentially a z-score. And if you've already looked at your, well, it wouldn't have it necessarily, sorry. But if you are familiar with the z-score calculation, and you should be, then essentially we're going to be figuring out what is my x. Is it going to look like this? X bar sub 1 minus x bar sub 2 minus mu sub 1 minus mu sub 2 all over. And then, we have this crazy complex thing going on down here, which is going to be, I don't even know if I want to try and think of it. It would be s sub 1 squared over n. No, I'm not even going to try and come up with that one right now. It's not coming to mind. But basically, as complicated as it might look, it's essentially just a z-score. And the reason I talk about this right now is that as you're reading your problem, the first thing you want to decide, are we talking about proportions or means? That's going to be the first big decision. So if it just says proportion, then that narrows it down right away. And later you're going to have some decisions to make. Is this one proportion or two proportions? Is this a confidence interval or is it a hypothesis test? But there are these kind of decision points. And the first one is it means or is it proportion? So that's kind of a good thing to know. And you've already seen that because we have a sampling distribution for means and a sampling distribution for proportions. And we handle them differently. Okay, so that brief aside over, let's jump into this. So we've got 0.325 is the proportion of adults. And we've got two simulations that's going to figure out the sampling conducted for the sampling distribution. And we're going to either have 1,500 trials with a sample size of 100 or 2,000 trials with a sample size of 50. And we want to talk about the center and the variability. And jumping right into it, the center does not change based on sample size. The center of this is just going to be your population proportion. So the mean of a sampling distribution of sample proportions is just the population proportion, which is in this case 0.325. Does not matter simulation A or B, those will be the same. So the centers will be equal. So I can rule out D and E. The question is, which one's going to have greater variability? Now we know that as you have, if this is your population distribution, a sampling distribution is going to be more compact, less spread out. And so that is one thing we did talk about. This is kind of just a reminder. And now the question isn't, how does this compare to the population mean distribution? It's how does this compare to the sampling distribution? Or sorry, how did the two simulations compare? And one thing that we learned is that your sample size, your standard deviation is inversely related to your sample size. So as your sample size goes up, your standard deviation goes down, and that can be seen in just the formula for it. So that is this right here, P times 1 minus P divided by N. Notice that N is in the denominator. So that means it's inversely related. So as N gets bigger, your standard deviation will get smaller and smaller. Not by a great deal necessarily, but it will get smaller. So bottom line, if simulation A has 100 sample size and simulation B has a 50 sample size, A is going to have a smaller standard deviation. So let me just write it this way. Standard deviation for A is going to be less than the standard deviation for B. And therefore, if we look, the variability of simulation A will be greater? No. Variability for A will be less than. Yes, there's our answer. And this just, this makes sense intuitively if we think about this. The average weight of a male is 170 pounds. I'm making this up. The average weight of a male is 170. If there's one dude who weighs 350 pounds, you're gonna be like, that happens. Sure, that's not weird. But if I told you we took a sample of 100 random men and got a sample mean of 350, be like, dang, how did that happen? You must have gotten like, how do you get a random sample that big, right? How do you get a sample mean of 100 men that averages out to 350? You know, maybe it's only offensive linemen in the NFL or something, but still. So if that just intuitively makes sense to you, that explains why when you have a big sample size, it's very likely going to fall close to the population mean. So I know I'm explaining all this just verbally, but hopefully that makes sense for you. All right, let's see what this one's all about. A recent survey indicated that the mean time spent on music streaming is 210 minutes per week for the population of a certain country. Simulation was conducted to create a sampling distribution of the sampling mean for population with a mean of 210. It shows this, we can see the results. Which of the following would be the best reason why the simulation of the sampling distribution is not approximately normal? Well, let's see. I mean, all right. So the samples were not selected at random. Does it say it was random? Recent survey. Now, I mean, it doesn't say whether it's random or not, but that wouldn't be the reason necessarily that it is not approximately normal. So that's almost certainly not the reasoning. And we can really just jump to the second one. The sample size was not sufficiently large. And that's really what it comes down to. I'm not going to read the other ones because remember, when you're dealing with proportions like we are here, these are means, I'm sorry. When you're talking about means, we have to make sure that the sample size is big enough. And for this, we have a rule, it's a central limit theorem that says that as long as you have a sample size of 30, you should get an approximately normal distribution for the sampling distribution. But maybe that didn't happen here. In fact, it looks like if these are just counting by ones, then, well, it's not. But whatever the case, somehow they didn't get a big enough sample size. The population distribution not being normal doesn't matter because the central limit theorem tells us that if our sample size is big enough, the sampling distribution will be normal. So that's not it. The samples were selected without replacement. As long as we didn't pick more than 10% of the population, the 10% condition takes care of that. All right. And the sample means were less than the population mean. That can happen. That doesn't determine whether or not, some sample means are less, some sample means are greater. So really the only good answer is B for this one. All right. This is a good conceptual one. All right, so imagine you have a population that follows this distribution, and these are proportions, or looks like, but anyways, it's some kind of data obtained about a population. All right, so here's the important thing. We can see that this is bimodal with a lot of people clustered at the low end and a lot of people clustered at the high end, and not very many in the middle. And this is, so we've got, now that's a population distribution. And what we're going to do is we're going to do a sample size of 2. Now, what's going to likely happen if I pick 2? Since we've got a lot of people clustered at the low end and a lot of people at the high end, there's really kind of 4 outcomes, right? So the first person can be at the low end or the high end, and the second person could be at the low end or the high end. All right, this is almost looks like your genetics Punnett square going on, right? So I could get some 2 people at the low end, and therefore my mean is going to be low. So I'll just put my sample mean right here. It's going to be low. I could have a high and a low, and so my sample mean here will be, I'll just put medium. A low and a high combined together is going to have a sample mean of medium. But if both of them came from the high end, which it seems pretty likely to happen, then the sample mean here is going to be high. So it looks like I'm going to have 3 distributions. Most people are going to be, or the majority, I don't know, majority is true, but the most common is going to be being right in the middle. But then there's going to be a cluster of people at the low end and a cluster of people at the high end. So the answer here is C. All right. So that's only true because we're dealing with sampling a sample size of 2. If this is a sample size of much bigger, 100 people, then we would probably see that kind of distribution. So just some fun stuff to deal with that. Okay. So now it's kind of hard to read this. It's hard for me to. I'm not wearing my glasses while I'm doing this. But we've got a recent report indicated that 90% of adults in a certain region actively tried to include vegetables in their diet. A simulation was conducted that consists of 50 trials with a population parameter of 0.9. Each trial consisted of a sample size of 10. The number of successes out of 10 was recorded, where the success report represented an adult trying to include vegetables in the diet. 5 possible simulation results are shown. Which simulation is the best match to the one described? So we need to, first of all, remember that we are running 50 trials of this. So the first takeaway before we look at anything else is that we should have 50 dots. So the only 2 that match in that case are C and E. I'm going to cross these out. It's not 10 trials, it's 50. I'm not counting those dots, but I can just visually tell those are 50. Now, maybe the next thing to look at is what is our response variable? We've already talked about simulations, and so response variable is like what value is actually being recorded at the end of the simulation. What's being recorded is the number of successes out of 10. Well, if I look at the scales here, the only difference between these is the scale at the bottom. The number of successes out of 10, that would be this right here. And just with that, I can decide E is correct. But it makes sense if we look at a little bit more, because you're not going to get 9 successes, even with a 90% parameter. You're not going to get 9 successes every time. You could get 10, could get as low as 7, right? And potentially you could get down even lower than that. But it's going to most commonly be 9 successes out of 10. And so it passes the kind of the logic test. All right. Approximately 52% of all recent births were boys, and a simple random sample of 100 recent births, 49 were boys, 51 were girls. The most likely explanation for the difference between the observed results and the expected results in this case is, well, I don't think in this case we have bias. I think the gender of a baby is definitely not something that you can introduce bias into, at least not yet. But anyways, it's not bias happening. Non-sampling error is not even a thing. We have non-response bias, but a sampling frame that is incomplete. Now, a sampling frame represents all of the possible outcomes. Male and female, let's just assume that those are the outcomes that are possible. And so that's not it. Confounding, really the purpose of this question is just to say, it's not always going to show up exactly like you'd expect, right? If 52%, according to population numbers, are going to be boys, well, a sample of 100 isn't going to be 52. It's the same thing we just talked about. 49 being boys, 51 girls is something you'd totally expect. All right. So that's just variability due to sampling. So to make that easy. All right. I don't know how many of these we're going to do. We can hang out till 2:30, but that doesn't sound like much fun. So let's just do a few more of these. And what I encourage you to do, we can look through more of these tomorrow. This is from the March, I'm trying to do my math, March 8th or 9th class? 8th, thanks. So this is a March 8th class. So if you want to look through the rest of these, if you have questions about any more, then we can do that. I think this is one that we've already seen something similar to. This is going to be talking about sample size. That one's, okay, this is maybe worth talking about. Okay. But anyways, if you want to look through the rest of these questions that we don't go through and you have any questions, I'm more than happy to go through any and all of these. But I don't necessarily want to go through all of them in class today. So which of the following pairs of sample size n and population proportion p would produce the greatest standard deviation for the sampling distribution of a sample proportion? Now you could just plug these numbers into the equation and figure out which is the biggest. But let's just look at this. Well, that's not how we write it. Let's look at the formula. The standard deviation for sampling distribution of sample proportions is, this is going to drive me insane, p times 1 minus p divided by n. So we know that for the greatest standard deviation, we want to have a low n. So the standard deviation goes up as the sample size goes down. So I want to get the smallest sample size that I can. So in this case, it's between 1,000 and 100. You can see those are the only options. I don't want the 1,000, I want the 100. And now the question is, do we want to be close to 0 or do we want to be close to 1/2? And this is one where you might intuitively figure it out. You might want to plug in some numbers, and there's nothing wrong with that. So we want the numerator to be as big as possible. We want the denominator to be as small as possible. We want the numerator to be as big as possible. So what gets us more? 0.5 times 0.5, which would be our p times 1 minus p, or 0.1 times 0.9. Which is bigger? Well, this gives me 0.25. This is 0.09. And so it gets bigger the closer we get to 0.5. So it turns out being as close to 1/2 as possible and having a sample size of 100 compared to 1,000 is going to give us our greatest standard deviation. Okay. Let's see if this one's worth talking about. Okay, this is just asking us to, it's asking two different things here. So the first thing it's asking us to do is just calculate the mean and the standard deviation. And it says that only 36% of eligible voters voted in the 2014 election. For a random sample of size 40, which is going to describe the sampling distribution of this. So to just straight up calculate it, we've already talked about this. The mean of our sampling distribution of sample proportions is just going to be the same as the population proportion, which is 0.36. So I can cross out B and E. Let me make sure I'm not reading this incorrectly. Okay, so it is, okay, that matches up. So that looks good. The next thing is the standard deviation for sampling distribution of proportions is going to be, we've already seen this formula a few times, so I already know this, the population proportion is 0.36, so it's going to be 0.36 times 0.64 divided by, it's a sample size of 40. So if I just, this is where we're just going to straight up use a calculator. All right. Now I can see who actually is using their calculator during class. I know right now it's kind of whatever, but you will be needing to use that calculator quite a bit. So I got 3. Oh. Oh, I did something wrong. Of course I did. So I was like, that does not look like a right answer. Let me change this real quick. Divided by, not multiplied by. There it is. When I did this, I got 0.076. So there we go. It's either A or C. And now the question, and this is why I wanted to look at this. If it was just calculating those two values, I would have just skipped it and said, you guys can figure that out. But the next part of this is, what is the distribution going to look like? Okay. And the way that we can figure this out, it's going to be approximately normal if it passes the large counts condition. So as a reminder, n times p and n times 1 minus p, both of these have to be greater than 10. And there are some people who get caught up on, does it have to be greater than 10 or greater than or equal to 10? I don't think it matters that much, okay? So it's going to be obviously one way or the other. So n times p, we have a sample size of 40 with a 0.36 population proportion. So 40 times 0.36 is 14.4. And 40 times 0.64 is going to be whatever's left over out of that, which is going to be 25.6. All right. So there it is. So both of these are greater than 10. So this is the test that we have to pass with proportions in order to make sure that it's going to be approximately normal. We passed it, so it's going to be approximately normal. If we did not meet it one way or the other, then we could decide if it's going to be skewed. Now, I will tell you with proportions, if you have a sample mean of 0.36 and it's skewed, here's 0, here's 1. If it's skewed, it has to be skewed to the right. It's always going to skew toward the opposite end. So it would skew toward 1, not toward 0, because here's the 50% mark. So bottom line, it would never be skewed to the left. I'll just tell you that. All right. I'm going to see if I can look through and find another good one to talk about. And maybe we can call it a day at 2 o'clock. Okay, that one you should be able to do. Is this means? That's proportions again. Another one with proportions, it looks like. No, sample mean. Okay, let's see how many I've got. I think that's the last one right there. All right, we'll do this one and call it a day. And I just wanted to have one that we were looking at means. So at a certain restaurant, the distribution of wait times between ordering a meal and receiving the meal has a mean of 11.4 and a standard deviation of 2.6. Sorry. The manager wants to find the probability that the mean wait time will be greater than 12 minutes for a random sample of 84 customers. Assuming the wait time among customers are independent, which of the following describes the sampling distribution of the sample mean wait time in random samples of size 84? So we want to figure out, first of all, is this going to be, we're describing the sampling distribution. And a sampling distribution, when you see that, just remember it's a normal distribution. Well, it should be if it meets certain conditions. But we're talking about something that looks like that. And maybe we can test that out first. Is it going to be normal? Approximately normal. And the only test for this when it's means is the sample size greater than or equal to 30? And we're doing a sample of 84. So we've passed that condition. It is not going to be binomial, and it wouldn't be skewed or anything else. So we're good on that. The next thing is that the sampling distribution will have the same mean. So the mean of our sampling distribution of sample means, is the same as the population mean. So it's going to be 11.4. All right, and that is this first sentence can be read as the population values because it's not related to a specific sample. It's talking about, this is just a fact about the restaurant, right? So 11.4 minutes, so we can cross this one out. So now the question is, what is the standard deviation going to be? And the standard deviation for a sampling distribution of sample means is just the population standard deviation divided by the square root of n. So that's 2.6 divided by the square root of 84. And now you can see that's right here. Okay. Now, I think the hardest part about this is like, I mean, maybe your own difficulties, if you have some, you'll figure those out on your own. But the hardest thing is, well, one of two things. One is figuring out if it's means or, what am I trying to say here? But basically, I'll just say it this way. I think the difficulty comes in with the fact that you need to set up a sampling distribution and you need to be able to identify the correct formulas to use. They are on the AP formula sheet, and maybe tomorrow what would be a good thing to do is just kind of look at the AP formula sheet again and just to say, I keep saying this is on the AP formula sheet, but we can just spend tomorrow a little bit of time saying, here's where it's found. Here's where this one is found. Here are all these formulas and where you can find them. And the one thing I want to remind you, and this will be the last thing, is the z-score is nowhere on the AP formula sheet, but there is a form of it that shows up there. All right. So that's one it's good to just have it memorized, but you've used it enough, you probably do. There's no homework for tonight, but I encourage you to look through this, look at your test corrections, see if you have any more questions about it, anything like that. I will probably not start with the new content until Monday, just to give you guys a little bit of time to get caught up and feel like you're back in the swing of things with statistics. So having said all that, have a wonderful day. I will see you guys tomorrow online, and I hope you have a good one. There we go.
See you tomorrow. Later.